Okay, so today we have the pleasure to have with us Cristina Cornelio, who is a researcher at Samsung AI in the UK. So she will talk to us about scientific discovery and derivable scientific discovery. So having a different way to combine algorithm for scientific discovery. So Cristina, welcome to Prairie seminar, and I give you the talking. So it's to you to talk.
Okay, thank you. Thank you for the introduction. Okay, so hi everybody. Today we'll talk about this project, Derivable Scientific Discovery, which was done in collaboration with my former colleague at IBM Research, where I was working prior to joining Samsung AI. So what's the goal of this project was to discover meaningful laws of nature in the symbolic form from experimental data. So what does this mean? Is, for example, if we have a phenomenon we are observing, for example, a satellite orbiting a planet, and we have a collection of data points, for example, the speed of the satellite, the distance from the planet, the measure of the masses of the two planets. From this collection of data point, we want to extract a formula that represents the orbital period, for example, of the satellite around the planet. So, and how can we do this? This can be done in many different ways, for example, using neural networks and statistical regression. And these are a very good method to discover patterns in the data. The problem with these methods is they are black box, so we cannot understand them fully. Other methods like standard regression, so this one is a little bit more interpretable, but the functional form has to be given. So we give the functional form and then we need to discover the parameters. And the last one, it could be symbolic regression, which is the tool that we actually use in our implementation, where the functional form is not given, but so from the data, we extract both the functional form and we fit the parameter to the data. So, and in these two methods, standard regression and symbolic regression, as I mentioned briefly, we have the plus that they are interpretable. So we can see the actual formula that describes the phenomenon. The problem with all these methods, including neural networks, is that even if we have the formula, we don't know if the formula matches what we know already about the phenomenon. For example, for the case of the planets, we might know the conservation of energy law or the conservation of momentum. So how can we know if one of these formula we extract from the data respects the background theory? So the collection of axioms that we know already about the environment we are studying. So our idea is that we can unify symbolic model extraction and formal reasoning. So because we want two capabilities. The first one, we want to know if the formulas we extract from the data can be deduced and verified with the axiom and the background theory. And the second one is that in the case these are not derivable, so in the case the formula are not derivable, we want to use the background theory to give us an estimate how good these formula are, not compared to the numerical data, but compared to the laws that we already know. So how close is my formula to the conservation of energy law with the conservation of momentum and so on. So what we did actually, it was to propose a new scientific method. So here we can see the top line in this slide is the classic scientific discovery method, which normally start with a generation of hypotheses from the theory. So we have the scientist that thinks, okay, this phenomenon can be maybe explained with this formula. Then the scientist tests this hypothesis on the data and see, okay, maybe the formula is not great, so I will modify the formula and obtain a better one and test again on the data to have this sort of a loop until we find we are satisfied and we have our new formula. Machine learning methods or regression methods, instead they just look at the data. So they look at the data, generate a formula, and this is it, right? So what we did with AI-Descartes, which is the new method we proposed, is to invert the classic scientific method while we start from the data. So we generate the hypothesis from the data, not from the theory, because now we have more powerful tools like machine learning, genetic algorithms, or symbolic regression. So we can generate the hypothesis directly from the data and then test this hypothesis on the theory. And also here we can have a loop until we are satisfied and we have our new formula. So, but how does our system work? So we start, as I mentioned, from the data and from the background theory. And the numerical data is a collection of the data points that describe the phenomenon, while the background theory is a collection of axioms that describe the laws we already know about a phenomenon. So first, we feed the numerical data to the symbolic discovery component of the system. This symbolic discovery component has the role of generate a list of hypotheses that fit the data in a different level of, with different level of accuracy. And this list is ordered based on this accuracy, so the numerical error on the data. So now we provide this list together with the background theory to the reasoning component. So the reasoning component then will re-rank this list of hypotheses based on how close these hypotheses are to the background theory. So, and given this re-ranked list of hypotheses, we can choose the best one, maybe even derivable, that we will use for the predictions. So in reality, the system is a little bit more complicated and has different components. But today I will focus mostly on the first one, which is the symbolic regression and the reasoning system, and how these two components related of each other. Okay. What is the input of the system? So the input is tuple of 4 elements, where the first element is the background theory, so what we call also background knowledge. So this is a collection of domain-specific axioms, which are represented as logical formulae. And this one represents the environment, so conservation of energy, conservation of momentum, condition of the equilibrium, and so on. And we have two assumptions about this background knowledge. The first one is the completeness. So we want that the background theory contains all the axioms that are necessary to explain a phenomenon. And the second assumption is the consistency. So we want the axioms that don't contradict each other. So these are this assumption, if you remember at the general view, we can also, in the case in which, for example, this is not complete, if we lose the complete assumption, we have some tools here to solve this problem, for example, using abductive reasoning, so that will kind of complete the background theory and then we'll start this loop again. But I will not talk about these other components today. Okay, so the second component in the input of the system is the hypothesis class. So this is a collection of rules that define the form of my hypothesis. For example, the grammar, so which symbols, which model, how to construct the models. The second one is the invariance constraints. For example, we don't want to generate two models that are equivalent. For example, if an operator is commutative, associative, and so on. The last one is the constraints on the functional form. For example, we want to generate only hypotheses that are monotonic functions. Okay, then the third component is the data, and this is just the collection of the data points. And the last one is the modeler preferences. So this one is a set of numerical parameters that defines, for example, the error bands on accuracy, error bands on complexity. So some parameters that guide the search a little bit. Okay, so let's start to talk about briefly about talking about the symbolic regression component of the system. To perform a symbolic regression, first we have to define a grammar. So the grammar is basically the collection of rules that define how we build the sentences in this specific language. And to define the grammar, we need to define the operators, for example, plus, minus, and so on. The operators we want to use in our hypothesis. For example, we can also restrict to only generate function that has only plus and minus, or we want to include a bigger set of operators. And the second one is the variables. So we want to define a set of variables we can use in the generation. For example, we can restrict to use only 2 variables, or we want up to 10 variables, and so on. And the last one is the constant we want to use. Okay, here are numerical constant, but constant can also be pi, the gravitational constant, and so on. Okay, so once we define the grammar, we can produce formulas like the example we see on the right here. And the bottom is the compact version of the same function that is expanded here on top. And so this can be also represented as like a parsing tree that we can see here. And if we represent it as a parsing tree, we can also have a definition of complexity. For example, the depth of the tree, the width of the tree, how many nodes the tree has, and so on. In our implementation, we use the depth of the tree, for example. Okay, okay, so this is the way we represented the optimization problem. So first, we start minimizing the fidelity on the data. So we want the model to be as close to the data as possible. And with these constraints, the first one is about the complexity. So we want to bound the complexity. For example, we only want to generate trees that has a depth of 5 or smaller or equal to 5. The second one is we constrain the grammar. So here we define that the model we create has to obey to the structural grammar and follow some symbols that we chose. For example, so this sigma star is a set of words in the language. So we first define the operators, the constants, and so on, and then the model has to obey to that. Then we impose the invariance constraints, and finally, we can also have a set of non-linear numerical expressions, which are other type of constraints. For example, we want the function to be equal to 0 in 0, and other constraints like that. So, and once we formulate our optimization problem as MeNLP, then we can solve this with like a solver, like a MeNLP solver. Okay, so then we go to the second component, which is the reasoning component. So we have 4 main reason capabilities. The first one is the derivability. This one is the one I mentioned before. So we want to know if a formula can be derived from the set of axioms defining the environment. For example, conservation of energy, conservation of momentum, and so on. The second one, this one is important in the case, especially in the case that the formula is not derivable. We define a set of reasoning measures. So this reasoning measure, they can be relative, absolute, and they compute the distance of formula extracted from the data to the background theory. So here, the important thing to notice is that this distance is computed with the background theory, considering the variable of interest. So the variable of interest is, for example, if you remember the example at the beginning where we had the satellite orbiting the planet. So here, the variable of interest is P. P represents the period. So the formula that we are looking for is P equal to some expression, right? So this formula then is implicitly defined in the background theory, but we don't see it explicitly. I will talk more about this later. Okay, so the third reasoning capability is the counterexample generation. So if we generate a formula that is not derivable, we can also generate with a theorem prover a set of new points that violate the current hypothesis. And these new points can be generated by starting from the axiom. So this is very useful to guide the search. And the last one is what we call constraint pre-processing. So here we have a different set of axioms. So this one are not logical axioms that describe the phenomenon, but are axioms that describe the functional form. For example, we want that the functional form is monotonic, or we want that the limit, if I go to infinity, then the limit is constant, and things like that. So what is important here is the difference between this type of constraints that are only on a functional form and contains only variables that are observable, while in the derivability part, the axiom in the background theory, they contain also variables that are not observed in the environment, and also contains laws that has nothing to do with the actual functional form that we are trying to extract. For example, if I'm trying to extract the period of the satellite orbiting a planet, the constraints could be that the function is monotonic, while the axiom are other laws like conservation of energy. Okay, now I'll talk a little bit more in details about the first capability and the second one, because are the ones that are more, we use more for experiments. Okay, for the derivability, we have two types of derivability we use. The first one is the direct, what we call direct derivability. That means I want to know if my set of axioms and constraints implies our formula that we extracted from the data. So here F is the formula we extracted with symbolic regression, which I described earlier. So for example, if we have this formula that's extracted from the data, we want to know if the constraints and axiom, conservation of energy and so on, implies my formula. Okay, so this is very nice, this type of derivability. The problem is that when we consider real world scenarios, this is very rarely satisfied because we have these constants, and these are numerical constants that might contain some errors. It can be not accurate enough, or can be a combination of existing constants like pi, the gravitational constant, and so on. So from the symbolic regression, we just have a number, but this number in reality can be a combination of symbols, or can be like of the wrong approximation. So this is why we introduce the existential derivability. So this one, what we want to understand if the functional form itself is correct. Sorry. So if the functional form is correct, can be correct even though the constants are not accurate. So what we try, for example, we see in the left, what we try to understand if exists two constants such that the axiom and constraints implies my functional form with these two constants. Then the two constants, I can run another algorithm to find the exact value, which could be this one. But what I'm trying to prove here, if the functional form itself is correct. So if the P is just a numerator and also the denominator and so on. Okay, so, but what happens if none of this formula, both with direct derivability and existential derivability, are not satisfied? Then we introduce what we call reasoning errors. So the reasoning errors compute the distance between a formula that is generated from the numerical data, which is the green one that you can see here in the figure, and the derivable formula that is implicitly defined in the background theory, which is the blue one here. So we want to compute the distance between these two functions. And what is important to mention, that I also introduced a little bit earlier, is that this blue function, we don't have it explicitly. So we cannot use just the regular, the standard distance between functions, because this one is encoded in the set of axioms. So in the axioms, maybe the P of the period of the satellite orbiting a planet is mentioned in many formulas, but we cannot generate all the possible formulas that start with P equal to something. But if we could enumerate all the possible derivative formula, then the right formula would be there. Just the number of all possible formula you can generate from an axiom set could be even infinite. So this is why we don't have it explicitly, but is represented by the variable of interest, which is P for the period in the example that I introduced before. Okay, so we define three types of reasoning errors. So the first one is what we call pointwise reasoning error. So this one computes the error between these two functions on the data points that we have in our data set. So this can be done with different type of norms and correspond to this formula that we can see on the bottom for the L2 norm. And this is computed via theorem prover. So we want to understand, we want to compute this distance without knowing the explicit functional form of the blue function here, which is the one that is implicitly defined by the axiom set. Then the second one is the generalization reasoning error. We want to compute the distance between these two functions between the data points. So if in the data set I have these 3 points, x1, x2, and x3, we want to know what happened in between, for example, x1 and x2, or in between here. So we want to have an estimate of the maximal distance of these two functions between the data points. And this also is done by a theorem prover and can be done because we have this second function implicitly defined by the axiom set. Okay, and this is a measure of how well the formula we extracted from the data generalize between the data points, so outside the domain. And the last reasoning error is we not only look at what happened in between the data points, but also what happened if I extend the domain of my variables. For example, if in the case of the planets orbiting the sun, we want to know what happened if instead of Jupiter, we have a much bigger planet, or we have a much smaller planet. So in this example we see on the right, we can see that this function is very good in the domain of the variables, but if I go beyond that, the error becomes to increase exponentially. So this third reasoning error is a way to measure how good the formula is, even outside, like order of magnitude bigger domain, right? And also, when we increase the domain, you usually do it by changing one single variable at a time. So in this example, we just have one variable, which is x. But as you can imagine, usually the function, they have many more variables, like in the planet orbiting the sun or a satellite orbiting a planet, we have 3 variables, which are the 2 masses of the 2 planets and the distance between them. So I change one variable at a time and see how the reasoning error changes, increasing the variable. And based on how, for example, if the error increases, we can also have some insight on how it increases, if it's increasing linearly, exponentially, or like so. And this is basically giving hints on, okay, maybe the variable X that I was changing in this particular moment, maybe should not be at the numerator, but should be at the denominator. Or instead of having a power of 2, should have a different power, a power of 3 or 4. So this can also give more insight. Okay, so now we, once we defined all this framework, we started to study 3 different showcases. So 2 from physics and 1 from chemistry. So what is common between all these showcases is that they are, we focus on real data. So we took real measurement, and that means we have a lot of noise. And also the type of noise is not as clean as in the simulated data. And the second characteristic is that we only have few data points. For example, in our experiment, we work as few as 10 data points. And then each of these, we chose these 3 specific problems because each of them has different challenging aspects. For example, Kepler. In Kepler's law, we have the masses of the planets that are very different. For example, if you consider the mass of the sun and the mass of one of the planets in the solar system, we can see that these 2 masses are order of magnitude different. So if I sum these 2 masses, basically the masses of the planets disappear. So this is very challenging. The second problem, Lagomir, sorry. So this one is challenging because it contains material dependence coefficients. And the last one, Einstein time dilation formula, this one is challenging because we consider 2 different background theory, and we use our tool to differentiate between these 2 background theory. One is from Newtonian axiom and the other from relativistic axiom. Okay, so now I will talk a little bit more in details about these 3 problems. But before doing that, I just give you a quick overview of the tools we use in the implementation. So for the symbolic regression, we use Baron as a MeNLP solver, and we use this set of operators. And we generated formulas that has a parsing tree at most depth, that has a most depth 7. And for the reasoning tool, we use, first we use Chimera. This one is a reasoning tool for dynamic system and is a combined different type of reasoning and has an underlying CAD system, which is Mathematica. And then we also use Mathematica for other type of analysis. For example, if you remember before, I mentioned this constrained pre-processing, but I will show you an example later. Okay, so let's start with the first use case. So the first one is the Kepler third law of planetary motion. This law relates the distance between 2 bodies and their orbital period. And the 2 bodies can be, for example, a star and the planets, or a planet and the satellite, or even 2 stars. So here you can see the formula that represents Kepler's third law, where P is the period, G is the gravitational constant, and then M1 and M2 are the 2 masses of the 2 bodies, and D is the distance between them. So just as an overview, a schematic overview of to recall how our system works, first we use symbolic regression. So for symbolic regression, we generate a list of hypotheses. So in this case, you can see I have 3 different data sets: the solar system, the exoplanets, and the binary stars. For each of them, I generate, in this slide at least, you can see 3 different hypotheses. And these hypotheses are ranked based on the numerical error. So now I use the reasoning tool, and the reasoning tool will compute the reasoning errors and check for derivability. And doing that, we can re-rank the list of hypotheses or even identify a derivable formula. Okay, so this is the background theory that we use for this problem. So as you can see, we have very how to say, known formulas, like the definition of a center of mass, the definition of distance between two bodies, the gravitational force, centrifugal force, and so on. And and this constitutes the background theory. This is a collection of axioms. So, and now we use the background theory to evaluate the formulas that we extracted from the data. So as you can see here is the same as before. We have these three different data sets. For each of them, I'm showing three different hypotheses. So if we look at the numerical error, we can see for the first data set, the first formula is the one with the lowest numerical error. For the second data set, we have the same. The first formula has the lowest numerical error. But if we consider the binary star data set, we can see that the first formula is the one with the lowest numerical error here. But just looking at it, you can understand this cannot be the right formula. This probably is also representing the noise in the data. So, but if we look at the reasoning error, we can see that the last formula is the one which has the lowest reasoning error. So we can identify this one as our final candidate. So, and this one is the one that has the highest numerical error between the three hypotheses that were my candidates. But if we look at the pointwise reasoning error, it's the one that has the lowest. And more importantly, if we look at the dependencies analysis, we can see that for all three the variables, the dependencies are satisfied. That means if I extend the domain of the variables from order of magnitude, the reasoning error doesn't change. So it stays constant. That means I have the right variables in the right position in the functional form. Okay, let's go to the second showcase. This comes from chemistry, and it was actually this formula won a Nobel Prize, I think, around 8 years ago. So this one is Lagrange absorption equation, and this equation describes the relationship between the loading on a surface, so how many molecules stick on a surface, and the pressure of a gas that is free in a certain container. So we have a container, we have an absorbent, which is a surface where the molecule can stick. And then we want to measure the relationship, like the rate of absorption between the gas or fluid and the absorbent depending on the pressure of the fluid in the container. So this is the formula that we can see here, and where Q is the loading on the surface, so the amount of molecules that are attached to the surface, and P is the pressure of the gas, and these are basically the two observable variables. And then there are some coefficient that depends on the material. So the function is this one, you can see here, where we related the gas pressure with the loading of the surface. This is the background theory that we use. And on the left, we can see the axioms that is, for example, site balance, the equilibrium assumption, and so on. And on the right, we can see another set of constraints on the functional form. If you remember before, I mentioned this is an important distinction because the background theory has laws that have nothing to do with the laws we're considering and we're studying. And I have also some variables, for example, the site number, they do not appear in the things I'm measuring during an experiment. So these are not observable variables. While in the constraints, I only have variables that I see in the experiment. In this case, it's only the pressure. And the constraints are on the functional form. So we have, for example, that in 0, the function has to be 0, because if you remember in this function here, we know that if we have 0 pressure of the fluid, then also none of the molecule will stick on the surface. because I don't have a force that push the molecules on the surface. And then we have also other constraints, for example, condition-netted limits and so on, monotonicity. Okay, so these are the the results of our experiments. As you can see, we have the collection of data points here on two different data sets. The first one and the second one different on the material of the absorbent, but also on the type of gas we are considering and the temperature. So just to recall how the functional form look like, the correct one. And we can see that many approximate my data points well, but some others, they don't generalize well between the data points. So we run the reasoning system, and we discovered that for the first data set, the function f2, so the orange one, is derivable. So we can see that is indeed the right one. That is exactly like here. It's go to zero. So when we have pressure zero, has zero loading and fits very well the data point. While other function like f7, it fits the points very well, but as soon as you go out of the domain, then it starts to have a strange behavior. While for the other data set, the G2, the orange, is the one that is derivable, but in this case is existentially derivable. So here, as you can see, the functional form is the right shape, but is not scaled well. So that means that one of the constants probably is not very good, does not have a good approximation. So we can rerun the system with this specific functional form and to tweak a little bit the constant to obtain the right function. Another thing to notice is that the function G5, so it's this purple one here, and the G7, which is the pink one, they are not derivable, but they satisfy all the constraints. If you remember, the constraints are this one, that in zero has to be zero, has to be monotonic, increasing, and the limit are bounded. So even with this, without looking at the background theory, just looking also at the constraints, we can see that we can re-rank this whole list of hypotheses with the derivable on top, but then we can also consider this as good approximations. Okay, and this is the last showcase. This is talks about the relativistic time dilation formula from Einstein. So, as you probably know, the Einstein theory of relativity says the speed of light is constant. So it cannot be, the light cannot go faster than that. So our experiments was considering two observers, on which one was stationary and one was moving at a certain speed v. And what we measure is the frequency of a light clock. One was stationary and one was moving with this speed v. Sorry. As you can see, the experiments, you can think about it as the light starting from the bottom of this figure, going to a mirror and then coming back. So in the stationary clock, the path of the light will be just these two perpendicular lines, while if the light clock is moving, then the path, of course, is a little bit longer. Okay, so the formula that describes this phenomenon that consider exactly the relative difference between the frequency of a light clock that is stationary and a light clock that is moving is described by this formula here, where v is the speed of the light clock and c is the light constant. So this is the correct formula. So we try to recover this formula from the numerical data, and we consider two different background theories. So the first background theory is the relativistic background theory, where the speed of light is a constant, while the second one is the Newtonian background theory, in which the speed of light is not a constant. So we don't have an upper bound on the speed of light. So as you can see, the main difference is this, the second axiom. The second axiom here, we can see at the denominator, we just have c, which is the speed of light, while here we can sum the speed of light with the speed of the clock. So then the light, in this case, has a speed that is greater than c. In the figure here on the left, we can see like in an animation that explains the two different background theories. So on the bottom, we can see the stationary clock as we saw before. So it just has these perpendicular lines. So in the relativistic case, we have that the speed of light is bounded. So it's a constant. So we can see that since the path is longer, will take longer time to arrive compared to the stationary clock. While in the Newtonian assumption, the speed of light is not bounded. So the amount of time that the light will take to go to the mirror and come back will be the same amount of time as the stationary clock, because I'm summing the two speeds, so the speed in this direction and the speed of light in this direction. So with our tool, AI-Descartes, we can identify which of these two theories explain the phenomenon better. And how we did this is by generating a set of hypotheses from the numerical data. So here on the left, we can see a set of 4 hypotheses, of which none of this is the right formula. So because we were not able to produce the right formula, but even with this set of formulas that are approximation of the right formula, we can see that there are some that approximate the data in a good way, then have worse reasoning errors. So, for example, the first one is the best one because it has a low numerical error, but also have a generalized reasoning error, which allows you to deal with speed of objects that go very close or even above the speed of light. And how we distinguish between the two different background theories is that we tried to compute the reasoning errors on all the formulas using the Newtonian background theory. And we noticed that all the formulas, independently of which one they have very bad, very high reasoning error. While if we use the relativistic, so the Einstein background theory, we see that all the formulas has lower error. So even though we don't have the right formula here, the formula that we produce from the data, which are approximations of the right formula, can give us an insight on which background theory describe the phenomenon better. Okay. Finally, the last experiment we did was to consider synthetic data set, because all these 3 use cases, like showcases that I described, we studied them in details, and the problem is that they have real data, so very few data points, very noisy, and so on. While what happens if we run our system on synthetic data? So there are many synthetic data sets. The problem is that they are not realistic. So in real life, we cannot take many measurements because it's making an experiment in the lab can be costly and also time consuming. And the noise on synthetic data set is very regular and very low. So, so they are kind of easier, this data set, compared to the real experiments that we performed in the example I showed you before. So, but anyway, we tried it just to compare with the state-of-the-art system. And we compared with these 4 systems. The first one, AI Feynman, is a deep learning-based method. The second one is Turing bot. This one is use simulating annealing. Then PSAI, this one use regularized evolution, annealing, and gradient-free optimization. And the last one is Bayesian machine scientists, which use Markov chain Monte Carlo methods. So then we tested these different methods on the Feynman synthetic dataset, which is a collection of many data points for each formula described in Feynman lectures. I mean, a subset of the formula described in the Feynman lecture. And we can see that our method outperformed the others, even on synthetic data. And the metric we use is accuracy, in the sense we took these formulas and we reduce the number of data points for each of the formula to make it more realistic. And we introduce noise, as they also propose in the AI Feynman paper. And then we compute the the percentage of these formulas we can recover from the data. And we can see that here we can recover around 60%, while the other methods can recover a smaller amount of formulas. And the second line, this is a subset of this data set, considering only the formulas that have at most two variables, dependent variables. And we did this because Turing Bot, at least the free available version, can only be run on maximum of two variables. So we did also this analysis, and we can see here that we still outperform the state of the art, but the difference is a little bit lower because these are easier problems. So since they are easier, also the other system can discover them. Okay, so with this, I conclude my talk. And if you want to know more about this topic, you can go on our website, which contains a lot of material, videos, animation, and so on. And of course, the link to the paper. And also, we open source the code, so you can take a look also at our GitHub repository. Thank you.
Thanks a lot, Cristina.
Thank you.
So, are there questions? Jérôme?
Yeah, so it's super interesting. And when you showed examples where you had several candidate functions, you clearly explained that first, you want to minimize errors, two kinds of errors, numerical errors, and then you have sort of a robustness criterion, if I understand well. But then what about the simplicity of the formula? Do you also take into account the simplicity of the formula?
Yeah. So this was so we encoded it in the complexity of the formula, if you remember.
Yes.
Let me go back. So we had different formulation. Okay. One of the slides at the beginning. Yeah, here. So here we bound the complexity, but what we do in reality is that we run this thing in with the different bounds. For example, if we consider the depth of the tree at most 7, we don't start with 7. We start with 2, then we increase to 3 until we have something that satisfy. So we also compute the the Pareto front between complexity and accuracy, or complexity and reasoning, and we take the Pareto front.
Okay, that was exactly my question. So thanks a lot.
Yeah, so we take also that into account. I think there was something in the chat. I don't know if it was a question.
Yes, maybe in the chat. Do you see a question in the chat?
No, it's more like if I can make available the slides. Yeah, okay. I will upload them. I will send it to you, also uploaded on the website. So.
Yes, so I find the approach very interesting. So I have also questions. When you generate the expression, you use linear programming. So this is So did you try other search algorithm for generating expression, or is it linear programming because you have a constant and you have to optimize the numerical values?
Yeah, so we use this MeNLP, so programming like tool, Baron. But so the good part of this this approach, I can show you here, is that many of these components you can like swap them with some different version. For example, here instead of symbolic regression, you can use genetic algorithm, for example, or you can use a neural network. So, or even the reasoning system. I mean, the concept themselves stay the same, which is the innovation of this paper. But the actual reasoning tool that you're using, like we use Chimera, but you can also use another theorem prover. So, but to answer your question, we didn't try to like ourselves to develop something new other than our symbolic regression approach. What we tried is that instead of symbolic regression, we integrated existing system in our pipeline. For example, if you remember, let me, okay. If you remember here, when we compare with the state of the art, so we try to integrate, for example, AI Feynman as a tool to generate the hypothesis. So each of these existing methods can be used instead of this part, the symbolic regression. So that we tried, and we can see that we are improving the performance of this algorithm because this existing algorithm, they generate many hypotheses, and maybe the right formula is there in this hypothesis list, but you don't have a reasoning system that tell you which one is the best one, which one is the right one.
Okay, thank you. I see. So if you want to try some search algorithm, we can replace the symbolic regression part and try it with your system, which is nice. And yes, for the Feynman data set, so you use some laws or some grammar or some deductive reasoning, but you have to define it for each formula. So for each
like
each
the
example.
background theory?
Yes. So you compared with on the Feynman dataset with your system with other system, but the other systems they don't have a theory.
So some system they try to integrate the theory. For example, there are some systems they are like a neural network, and they integrate these constraints in the loss, for example. So, but this is not a hard imposition of these constraints. Also, they can only use this type of constraints here, because this one are constraints on the functional form. So if I put like a parameter, for example, in the loss function of a neural network during training, and we can put a penalty if I violate this constraint or a penalty for this constraint, then of course the solution you generate will be closer to this constraint. But this other, the background theory constraints, this is a little bit more tricky to include them. So the other system, they try to do something like that, but it's kind of always a soft version of imposition.
Okay, but for the Feynman dataset, you have to write a background theory for each dataset. Okay.
Yeah, this is one of the kind of drawback of this of the current approach is that for each system you need to collect the axioms. So, but this can be done manually, like we did, because we had 3 problems, and also this other one that we consider here. But in general, you can also extract it like automatically using large language model, or you can like you know, if you ingest like a corpus like physics books, you can extract all the formulas automatically.
Okay, yes, these are physics formulas, so yes, they are well known.
Yeah.
Okay. Are there other questions? So I think there are questions by Quentin Marcoux.
read it.
Do you read it?
Okay.
So he says that if you can also search the constraint space, so he understands that you can compute a closed form solution for an observable, but for a dynamical process, can you search the dynamical system differential equation that lead to this observable closed form solution?
Not sure. Understand. Let me read again. Also an example. I see. Okay, so this is related to kind of abductive reasoning, if I understand. So I'm searching for the equation derived from the data, but also the axiom themselves, if I understood correctly. So in that case, I mean, I have to start with some background theory. I can use maybe abductive reasoning to generate it. We're also at the moment developing another system that allows you to have also an incomplete background theory and will kind of compensate for the missing axiom, put it in the, like in the, how do you call it, the reminder of the equation. Not reminder, how it's called, the rest. But so in this particular paper, we didn't do that. What we did is to try to integrate it with abductive reasoning. In that case, you can also search through the constraints. But yeah, I don't know if this answered the question.
Quentin?
Okay.
Yes, he says thank you. Okay, great.
Yeah, you can also contact, like send me an email afterwards, actually, if you have other, like if I didn't explain very well, we can also have an offline discussion.
Okay, so I think we can now close the meeting. Or are there other questions? Okay, so thanks a lot again, Cristina. It was a wonderful talk. So we're happy to have you.
Thank you for inviting me.
So I will stop the recording.
Okay.
So
Okay. Thank you.
bye.
Bye.